Welcome back to our ongoing deep dive into the OEIS, the Online Encyclopedia of Integer Sequences.
It's great to be back.
Today, we'll be looking at A000086.
Yeah, it's a really cool example of how, something that looks pretty simple in math can actually lead to some pretty unexpected connections.
Very interesting.
It all starts with a congruence equation.
Uh.
XLX plus 1A0 bay n.
Okay.
So you're essentially trying to find values of x that when you plug them into that equation, the result's a number that's divisible by n.
Okay, so for those of our listeners who might not be as familiar with modular arithmetic, could you break that down a little bit further for us? What does congruent modulo n actually mean?
Sure. Think of it like a clock.
Okay.
In modular arithmetic, all we really care about are the remainders you get after you divide.
Okay.
So, for example, 9 is congruent to 2 modulo 7 because they both have a remainder of 2 when you divide them by 7.
Okay, that makes sense. So in this sequence, if n is 7, we're looking for numbers that when we plug them into x squared x plus 1, they give us a result that leaves no remainder when divided by 7.
Exactly. And if you play around with some numbers, you'll see that 3 and 4 fit the bill.
Okay.
So 3 squared minus 3 plus 1 equals 7.
Right.
Which is obviously divisible by 7. And then 4 squared minus 4 plus 1 is 13, which also doesn't leave a remainder when you divide by 7.
Interesting. Now, the OEIS entry also mentions an equivalent form of the equation, which is x squared plus x plus 1 era mod n. What makes those two equations equivalent in this context?
Yeah, so the key here is that the roots of those two equations, they only differ by 1.
Okay.
So if you find a solution for one, you can just add or subtract one, and you'll get a solution for the other, at least in terms of their remainders modulo n.
Oh, okay. I see.
So it's kind of like two sides of the same coin, just shifted a little bit.
Right. Now, before we get into some of the more complex aspects of this sequence, let's talk about a really key property that makes it super interesting. A000086 is multiplicative.
Yeah.
So can you tell us what that means exactly?
Sure. So it means that if you have two relatively prime numbers, let's call them m and n, the sequence value for their product, so m times n, is equal to the product of the sequence values for m and n individually.
So why is this multiplicative property so important? What does that actually tell us about the sequence?
It's important because it makes it way easier to understand the sequence.
Oh.
We only really need to figure out how it acts for prime numbers.
Okay.
And then from there, we can figure out how it acts for any number just by breaking that number down into its prime factors.
That's a pretty neat shortcut. So let's talk about those prime numbers. The OEIS entry gives some very specific rules for how A000086 behaves at prime powers.
Right.
Can you walk us through those?
Absolutely. So let's start with the simplest case. When we have a prime number p raised to a power e, so p to the e. If p is 3 and e is 1, meaning we're just looking at the prime number 3 itself, the sequence value is 1.
Okay.
However, if we increase the power of 3, so e is now greater than 1, then the sequence value becomes 0.
Oh, okay. So for 9, 27, 81, and so on, the sequence value is always going to be 0.
Exactly.
Gotcha. Okay.
Now, for primes that leave a remainder of 1 when you divide them by 3, so primes like 7, 13, or 19, the sequence value is always 2.
And what about primes that leave a remainder of 2 when divided by 3? So like 2, 5, or 11?
For those primes, the sequence value is 0. And you might have noticed something interesting here. All the values we've seen so far are either 0 or a power of 2.
Now that you mention it, that is a really interesting pattern. Is there a deeper reason for that, or is that just a coincidence?
It's not a coincidence at all. This actually hints at a connection to a really cool area of math called field extensions.
Field extensions. I have to admit that's not exactly my area of expertise. Could you shed a little bit of light on how those relate to our sequence?
Sure. So in a nutshell, field extensions involve extending a set of numbers by adding new elements to it. Think of it like building an addition onto a house.
Okay.
And in this case, the solutions to our congruence equation can be thought of as living in certain field extensions of the rational numbers.
So we're not just dealing with simple remainders anymore. We're venturing into the realm of abstract algebra.
Exactly. And the fact that our sequence values are just 0 and powers of 2, it kind of suggests that the solutions to the equation, when they do exist, they form groups with sizes that are powers of 2.
Wow, so it's fascinating how this simple equation about remainders can lead us to these much more complex mathematical concepts.
Yeah, that's the beauty of math. It's all interconnected in these really surprising ways.
Speaking of connections, I noticed that the OEIS entry mentions a link to another sequence, a 001615.
Yes.
Can you tell us about that connection?
Sure. So A001615 is a sequence related to something called the totient function, and this function counts how many positive integers less than a given number are relatively prime to it.
Okay.
And what's interesting is that A000086 is always congruent to A001615 modulo 3.
So for any given n, if we take the values from both sequences and we divide them by 3, they'll always have the same remainder.
Precisely.
Could you give us an example just to illustrate that?
Of course, let's take n10 as an example. The 10th value in A00000086 is 2.
Okay.
And the 10th value in A00001615 is 4.
All right.
Well, both 2 and 4, they leave a remainder of 2 when you divide them by 3.
That's a pretty neat connection. Is like these two totally separate sequences have this like hidden relationship, a mathematical kinship.
Absolutely. And the OEIS is just full of these amazing connections. It's constantly revealing these hidden relationships between mathematical concepts that you might not think are connected at all.
Now, before we move on, I can't help but notice we've mentioned elliptic curves a couple of times already. The OEIS entry says that A000086 actually counts certain points on these curves. Can you tell us a bit more about that?
Yeah, so A000006, it actually gives us the number of what we call elliptic points of order 3 for the modular group gamma 0n. Now, to fully understand what that means, we need to dive a little bit deeper into the world of elliptic curves.
And that sounds like a perfect place to pick up in part 2 of our deep dive into A000006. We'll be back after a short break.
Welcome back. So elliptic curves, they're kind of these geometric objects that are defined by specific equations. And what makes them so interesting is that you can define a kind of addition on their points.
Okay.
Which gives you a really rich structure to work with.
Okay, so we're not just talking about simple addition, like 1 + 1 = 2. This is a more abstract kind of addition specific to elliptic curves.
Exactly. And A000006 is telling us something about the points on these curves that have a specific order. So specifically, it's counting the points of order 3, which means that if you add that point to itself 3 times, you get back to the starting point.
So the seemingly simple sequence about remainders can actually tell us something about the structure of these more complex geometric objects.
Yeah, it really does. And this highlights just how interconnected seemingly very different areas of math can be. Now, there's another fascinating connection mentioned in the OEIS entry. It's the sequence's asymptotic mean.
Okay. What can you tell us about that?
Right. So the asymptotic mean basically describes the average behavior of a sequence as you go further down the line.
Okay.
For A000086, it's about 0.367552.
So if we look at larger and larger values of n, the average number of solutions to our original equation will get closer and closer to that number.
Yeah, exactly. It kind of gives us a sense of how often we should expect to find solutions as n gets bigger and bigger. Now, remember that connection to A000000 we talked about before?
Yeah, I do.
Well, A000086 isn't just connected to that sequence. It also has connections to sequences that deal with polygonal numbers and even sublattice enumeration.
So now we're talking about geometric shapes and lattices. This is really taking us on a mathematical journey.
It is. And the OEIS is just a treasure trove of these types of connections. It reveals these hidden relationships between mathematical concepts that seem totally unrelated at first glance.
Now, going back to what we were discussing earlier, you mentioned that the pattern of just having zeros and powers of 2 in our sequence, that hints at something deeper. You talked about field extensions.
Right.
But I'm still not entirely clear on how those two things are related.
Okay, sure. It is a little bit of a jump, but it's definitely worth trying to wrap your head around. So you remember how I said that field extensions are basically like adding new elements to a set of numbers? Well, imagine you start with just the rational numbers. So all the numbers that can be written as fractions.
Okay, got it.
Now, let's say you want to extend this set by including numbers that solve certain polynomial equations, just like our congruence equation. Now, sometimes those new numbers can be expressed using just those rational numbers we started with.
Right.
But sometimes you need to introduce totally new types of numbers.
So interesting. So it's kind of like we're adding on a new wing to our mathematical house to make room for these kind of more unusual numbers.
That's a great way to put it. And the way that these new numbers interact with each other, the structure of how you can add them together, it's often reflected in the pattern of solutions to that original equation.
So in the case of A000006, that pattern is the zeros and the powers of 2.
Exactly. The fact that we only see those values kind of suggests that the solutions, when they exist, form groups with sizes that are powers of 2.
Wow.
It's like a little peek into how these extended number systems are put together.
That's pretty amazing.
Yeah.
It seems like we've started by just counting solutions to a really basic equation, and we've somehow ended up exploring the structure of like these abstract mathematical spaces. Yeah, there was one more thing you mentioned before that I wanted to touch on, the shadow transform.
Oh, yes, the shadow transform. So that's basically a mathematical operation that can link different sequences together,
Okay.
sometimes in really surprising ways.
Interesting.
And in this case, it actually connects A000086 to A000061.
Okay.
And that sequence is the sequence of central polygonal numbers.
Central polygonal numbers. I think I vaguely remember those from geometry class. Aren't those the numbers you get when you arrange dots into like different shapes?
Yeah, exactly. So think of like a single dot.
Okay.
And then you build a triangle, a square, a pentagon, all made up of dots around that center dot.
Okay, I can picture that. So the central polygonal number for a triangle would be 4, right?
Yes.
1 for the center dot and then 3 for the triangle itself.
Exactly.
Okay, and then for a square, it'd be 5, 1 plus 4.
Precisely. And A002061 lists out all of those numbers, 1, 4, 5, 7, 10, and so on. And somehow, through this thing called the shadow transform, that sequence is connected to our sequence about solutions to a congruence equation.
That's pretty wild. It's amazing how the OEIS can reveal all these hidden connections between these seemingly unrelated mathematical objects.
It really is. And this just goes to show that math isn't just a bunch of different topics. It's a big, beautiful, interconnected web of ideas. It's like this tapestry woven from lots of different threads.
Well, I think we've covered a lot in our deep dive into A00000006 today. Modular arithmetic, prime numbers, field extensions, elliptic curves, and even polygonal numbers, and the shadow transform. But before we wrap up, I want to leave our listeners with something to think about.
Okay.
We've seen how changing that original equation just a tiny bit can create completely new sequences in the OEIS.
Right.
But what if, instead of changing the equation, we change the question we're asking?
Mm-hmm.
What if, instead of just counting the number of solutions to that equation, we actually look at the structure of those solutions themselves?
Whoa, that's a really interesting idea. It's like we're opening up a whole new avenue to explore. We could see if those solutions create any kind of interesting structures.
Right, exactly, like groups or rings.
Exactly. We could figure out how the structure of the solutions changes as we change it.
Yeah, exactly. It's like we've opened up a whole new room in the house of mathematics just by changing how we're looking at things.
And that's what makes exploring mathematics so exciting. There's always something new to discover, a new question to ask.
So, to all of our listeners out there, I encourage you to keep exploring. Don't just take the OEIS entries at face value.
Dive in.
Pick a sequence that grabs your attention.
See what connections you can find.
Ask your own questions.
You can see what you can discover.
You never know. You might just stumble upon something amazing.
And remember, the OEIS is alive. It's constantly growing and changing thanks to all the curious mathematicians and enthusiasts around the world.
So go out there, explore, and who knows, maybe you'll make your own mathematical discovery.
Until next time, happy exploring.
Okay, so as we wrap up our exploration of A00000006 today, let's take a minute to think about what we've actually learned.
Yeah, it's been quite a journey.
It has.
We started with a pretty simple equation. X rocks let's plus 1 is 0 mod n.
Right.
Just looking for numbers that fit certain divisibility rules.
Yeah, and from there, we went on this incredible journey through all these different mathematical ideas.
We did.
We saw how that multiplicative property of the sequence really helped us unlock its secrets. Like we could just focus on how prime numbers worked and then figure everything else out.
Exactly.
And then we got into those specific rules for prime powers,
Right.
which showed us that really interesting pattern,
Yeah.
all those sequence values being either 0 or a power of 2.
It's pretty cool, right?
It is. And that pattern actually hinted at this whole other connection to field extensions.
Yeah.
Where we're expanding the world of rational numbers to include these more exotic solutions.
Exactly.
We also explored links to other sequences in the OEIS, like A00008615, which was connected to the totient function, and A000061.
Right, the central polygonal numbers.
Yeah, which really showed us that, all these different parts of math are really interconnected in these surprising ways.
Definitely.
We even talked a little bit about, elliptic curves.
Oh, yeah, those are fascinating.
And how A000086 can actually give us information about, the structure of these really cool geometric shapes.
Yeah, it's amazing how much depth there is to this sequence, even though it starts with something so simple.
I know. It's been a really fun deep dive. But before we go, I want to, encourage all of our listeners to keep exploring the OEIS.
Definitely. There's so much more to discover out there.
So much. Pick a sequence, any sequence.
Yeah, it doesn't matter where you start.
Look for those connections.
Ask those questions.
Math isn't just stuck in textbooks.
No, it's a living, breathing thing.
Exactly. It's constantly changing and growing thanks to all the curious minds out there.
It really is.
So go out there, explore, and you might just find something amazing.
And who knows, you might even make a discovery of your own.
Until next time, happy exploring.